Good morning to all of you. I am Nimesh Heshan Veeravarna, who is a graduate student at Memorial University, Newfoundland, Canada. Today I am going to discuss about a solution for power transformers. In here I am going to discuss about differential protection of power transformers using MATLAB. So let's move on to the outline of today's discussion. In here there are 7 points which I am going to discuss today. Introduction, problem statement, literature review, background of the study and methodology, modeling and simulation, results and discussion, and the conclusion. Without any further explanation, let's move on to the first topic. Around the turn of century, the first electromechanical overcurrent relays was installed and the power system protection was established. As the figure in the presentation, the majority of the protection principles employed in the protection relays today, including an overcurrent, directional, distance, and differential protection, were developed in the first 3 decades of 20th century. The development of relay technology, including materials, components, and the manufacturing process of the relay protection devices, physical structures, has been supported by modern science and technology, notable electronic and computer technologies. Simultaneously, majority theoretical improvements in the relay protection software, algorithm, and other areas has been made. As the figure in the presentation, the advent of modern technology pushes the development of power system protection. Relay protection progressed through several stages of development between the turn of the century and the end of 1990s, ranging from electromechanical to semiconductor, then to integrated circuit and microprocessor technology. Microprocessor-based digital and numerical relays are quickly replacing conventional relays in today's power system protection. Despite that, many of original protective relays principles are still in use today. In the late 1960s, a centralized substation protection system based on centralized computer system was suggested. In this watershed moment in the history of power system security, the approach is consistent with the conception of overall integrated protection, in which the protection package could not only individual plant until but also network segment. However, the concept was not widely embraced until recent, since there was no readily available computer hardware or software or communication technologies to enable it. Because of the usage of digital means, relay technologies has advanced rapidly since then. In the 1980s, the integration of microprocessor into system was often accomplished through the use of distributed processing platform that focused on safeguarding individual system components. Substation power transformers are the most expensive and critical piece of the equipment. They are also important of producing station output voltage and in general for the proper operation of the electrical power system. They are used step up or step down transmission voltages and are regarded to be extremely dependable equipment. During the normal operation, the transformer windings and core are subject to vary of stresses including vibration, temperature cycling and expansion and contraction. The magnetic flow causes warming, heat and owing to overload or poor cooling forces related to fault currents. When the transformer fails, the consequences are generally severe. The transformer may need to be transferred for repair in some situation, depending on its size, which might take long time. The goal of this academic study is to come to a conclusion on challenges in power transform protection and propose practical remedies. The transform protection major goal is to identify internal faults in the transformer with a high degree of sensitivity and induce subsequent de-energization while remaining resistant to external faults such as wire faults. Sensitivity detection and the de-energization restrict fault damage and hence the number of repairs required. It should, however, be able to offer backup protection in the event of system through faults. Since these can cause degradation and accelerated aging as well as failure of the transformer winding insulation on into overheating and high impact pressures induced by a high volt current in the winding. Aside from internal protection, abnormal system circumstances such as overexcitation, overvoltage, and cooling losses can cause degradation, accelerated aging, and internal transform failure. As a result, protection against these failures should be included in the overall transformer protection plan. Moving to the next slide shows the literature review. In 1971, the basic principles of digital compute operation for power transform protection were established. The harmonic resistance techniques to different protection. Digital filters are used to discriminate among the faults and magnetizing inrush currents. The filters are made up of the fundamentals and second harmonic content of measured different currents. This document the recommend system offline testing. In 1998, the technique of calculating inrush current was published based on the least square curve filtering for the recorded differential current and the evaluation of DC and fundamental up to harmonic components. The frequency of the second harmonic component as well as the significant aspect of the differential current are used to detect the inrush current. In 1982, a rapid and a delicate power transform protection method was built using rectangular transform technique. A crucial equipment for successful power system relay utilizing microprocessors is a quick and accelerated computation using a simple mechanism. To produce Fourier coefficient, just the adding and subtracting method is used. The non-zero differential current produced by power transformer stimulation and that produced by inner fault are well matched using this method. Using a second or a high harmonic component, this method has been employed to provide quick defect detection. In 1988, an enhanced digitalization differential relay for safeguarding a three-phase power transformers were designed and built using Kalman filters theory. In 1998, Kalman filters for three-phase power transformers were developed and implemented in real time utilizing a digital difference and earth fault avoidance technique. The components of fundamentals, second and the up fifth harmonic of the power transform current were determined using 11-state Kalman filters. In 1992, three approaches of large number of disturbance of power transformer stimulation were employed to evaluate the influence of undetected internal defects generated by second harmonic response of differential current on power transform protection. test of experimental transformers that was used to acquire sample data online. A novel approach has been applied to improve the detection of the internal faults at the power transformer. In 1997, it has hypothesized that artificial neural networks may be used to develop a digitalization power transform protection. This technique has been utilized for inrush current disclose the numerical protection of available. However, it is unreliable. Furthermore, an artificial neural network was used to reconfigure distorted current transformer currents on the secondary side due to a saturation. In 2002, a velvet-based numerical differential protection technique was disclosed, and it was used to protect the power transformer utilizing a harmonic resistant approach. Internal flaws are distinguished in the piece and computerly efficient way using magnetizing overcurrent and overexcited inrush in this software. The digitalization differential protection of three-phase power transformers and improved method based on harmonic and differential current treatment was given in 2004. Variable component attitudes for a second harmonic differential current during disturbance and inrush current occurrence when taken into account when developing this method. In this method, a reference function was established for the differential current in terms of time based on the difference of component of the second harmonics. By speculating on the signal of this criteria function for three phases, the internal disturbance may be precisely distinguished from inrush current situation. The primary advantage of the procedure is that this is accomplished within the period of around half a cycle following the disruption event. The disturbance reveal techniques does not build on the selected thresholds, which is second advantage of the better method suggested in this study. Using the PSCAD EMTGC program, this enhanced system has been developed and tested to account for functional variables on differential current components. In 2011, this research developed software for Fourier transform dependent logic techniques for power transform protection. This application was designed to simulate and evaluate the digitalized differential relay for electrical power transform in variety of operating scenarios. The problem of severe excitation of power transformer differential protection system using an external disturbance is addressed in 2019. During an external disturbance, the protective tripping current automatically rise. The differential protection reliability is improved by using the phase comparison approach for current in the protection end and the planning restraining. For increased differential protection, a logical scheme of algorithm and formula was devised from allocating the qualification of operation. The suggested restraining model with phase comparison percepts was tested in the protected zone using the MATLAB SIMULINK environment. The result shows that the likelihood of erroneous tripping during outer fault length is reduced by over tenfold when compared to non-restraining methods and is as low as 2% in the most severe modes. Moving to the next slide shows the background of the study and the methodology. A fuse protection system is a simple and expensive, yet differential protection has various advantages over the protection system, which is why they employ it. These advantages included differential protection detects fault faster than the other methods and decrease damages caused by the fault current flow. Depending on the size of the protection zone, the differential protection system may pinpoint the exact spot. Accurate fault location allows the user's automation techniques such as fast separation of faulty components and the load restoration. The Bachelor's relay may detect transformer faults that originated inside the insulating oil. The relay, on the other hand, will detect a fault in the transformer if it is not occur in the oil. Moving to the next slide, the differential protection method is based on the simple conceptual technique. As you can see in the figure, display the basic block diagram. The differential relay differentiate between the power transformer, transformer primary and secondary current, and its imbalance is detected. The relay will act and trip both transformers, primary and secondary circuit breakers. Current transformers on the both sides of the winding is required for differential protection. As needed, the differential protection system compensates for a phase difference between the line current on each side of power transformer. Moving to the methodology, differential protection for power transformer utilizing the relay is given in the study. The MATLAB SIMULINK platform was used to investigate the vast power transformer differential protection relay, and the main idea is to safeguard the power transformer from internal defects and keep it from being distributed by external factors. The power transform relay may trip time was created according to an external source, which will create a discrete signal to trip the breaker. The collected results show that the proposed differential relay is suitable course of action. Inrush fault and no fault states might all be distinguished by the suggested relay. Moving to the module and simulation, I have created the MATLAB Simulink block diagram in here. As we can see the three-phase power and the transformers, breakers, and this is what I use a discrete signal to trip the circuit breaker. The data of the research was taken from the Airport Aviation Services Limited, Sri Lanka, while I'm doing my internship. So the nominal power is 250 megawatt and nominal frequency is 50 hertz. Winding 1 parameters V1 phase to phase 11 kilowatts, R1 0.002 ohms, and the inductor is 0.08 pu. Winding for second parameter phase to phase VRMS is 33 kV and the R2 is 0.022 and the inductor was 0.08. And this is the subsystem of the power differential power protection. Moving on to the results and discussion, I have created two cases. One is case 1. As you can see, at no fault condition, the simulation results for voltage and current for the primary and secondary have stated in here. So this is the primary side voltage. As you can see, there are 3 phases over there, and there is no issue with this. In here you can see the current, the diagram, current versus time in the primary side. As you can see, there is no any issue since there is no any fault in the primary side at the moment. This is the secondary side of the transformer, and this is the secondary voltage at receiving transformer side. So as the case one is, there is no any faults, the voltages and the currents are not appearing any faults. In here the diagram states current versus time, secondary side current at receiving transformer. Moving to the case 2, I have, as I mentioned earlier, I have created a discrete signal to trip the circuit. So I have inserted the signal, and you can, as you can see in the diagram, the voltage signals when the type of fault is 3 phases to ground. So as you can see, there is a single line over the all 3 phases as the fault is appear in the system. More into the current diagram on the primary side. As you can see, when the faults appear, the phase currents go higher than the nominal current. So in this slide shows the secondary side of the transformer, which once the faults occur, the system illustrate a fault in the secondary side. And this diagram states the current at the secondary side of the transformer, which you can see. Moving to the summary of this presentation. In this research, I have MATLAB and Simulink is used to improve the differential relay features. Differential efficiency was examined at the site with the 3-phase fault, and the numerous faults that occur in the power system were investigated. The current and the voltage typical scenario where no faults, no problems happen, as illustrated in the case 1. As shown in the case 2, if an internal fault occurs in the transformer sending side, the differential relay will send a signal to circuit breaker at a time which I have investigated as 0.1 seconds, causing the circuit breaker to open because the current signal of the current transformer and transformer is not identical as the result of relay operation. So this is my end of my presentation, and thank you. Have a good day.